Hello, my name is ZhengYuqing, and today I will introduce you about my final project, the real-time emotion recognition from camera with deep CNNs. And this project explores how convolutional neural networks can be applied for facial emotion recognition in real time using simple hardware like a webcam and a laptop. I implemented this project by using the source code from MATLAB community from ZhengYuqing, and you can download the whole original project from this link. So imagine a classroom where a system can detect if students are confused, or a driver monitoring system that recognizes fatigue or anger in real time. Facial emotion recognition enables machines to respond empathetically and contextually. And with the right tools, such systems can run in real time on everyday devices like laptops and webcams. So we can generate this application to detect our facial emotion. Let's quickly overview our workflow. The first step is to download the dataset from the kaggle.com using this link. So you can see the dataset has 7 emotion classes, which are angry, contempt, disgust, fear, happy, sadness, and surprise. The step 2 is to process the image loaded into an image data store for easy manipulation and split into training and validation sets. The third step is to use a customized CNN defined with convolutional layer pooling and fully connected layers. The fourth step is to train the model. I use the adaptive moment estimation optimizer. The fifth step is to validate how the model strengths, the accuracy, and the confusion metrics are used to evaluate the model's performance. The sixth part is to integrate the camera. The trained model is deployed to classify emotions from live webcam input. So in this part, I will illustrate my CNN model design. As we all know, the convolutional neural network is one of the most central techniques in image processing and expression cognition today. CNNs are able to simulate the human visual system and automatically learn important regions and features from images. Facial expression recognition needs to deal with complex visual features such as subtle facial muscle movements, detailed structures, and local textures. You can see all the layers in my project. The first few convolutional layers of the CNN are responsible for extracting the underlying features such as skin surface texture, wrinkles, tensions, tiny spots, rough areas. The convolutional kernel learns in a manner similar to a Gabor filter, automatically generating a feature map that adapts to changes in edges and frequencies. Batch normalization and ReLU activation functions help the model to be sensitive high-frequency texture regions. The intermediate convolutional layer focuses on mesoscale features. They can extract symmetry information from regions such as eyes, mouth, and nose, eyebrows. Symmetry modeling is particularly important, and the ability to perceive symmetrical regions of the face can be enhanced in CNNs through dual-channel feature map comparison, parallel convolutional structures with shared weights, or the introduction of dilated convolution. It can be also combined with spatial attention to strengthen the focus on specific regions. The posterior layer of the CNN integrates all local features through a fully connected layer to form a high-level semantic vector. The classification probabilities of 7 typical emotions are output using softmax layer. This stage can also be combined with attention mechanism to focus on high-weighted regions, such as zygomatic bone lifting and eyebrow bending, which have significant differentiation in expression discrimination. To improve the temporal consistency of expression change modeling, some models also integrate long short-term memory networks or temporal convolutional structures to support the continuous recognition of dynamic expressions in video sequences. The next part, I will introduce you my training and my optimization. Well, different fixed learning rates such as 0.02, 0.01, and so on were tried sequentially with epoch set to 100. The results show that the model with learning rate of 0.005 performs best on the validation set, balancing coverage speed and for the epochs number. We can see at 20 epochs, the learning sample size is too small for the model to learn sufficiently, and the accuracy of the validation set is low. Only around 80%. When the epoch set to 30 to 50, the model has learned sufficiently, but the validator accuracy is slightly lacking. For 80 epochs, the model performance improves significantly. The model learns sufficiently, and the validator accuracy reaches about 99%. When I increase the epoch to 100 and 200, the improvement of the validator accuracy is stabilized, but it takes too long and overfitting occurs in some cases. So at the end of the test, I set my configuration to 80 epochs. Learning rate is 0.005. I choose the ADM optimizer because from some periodical it shows that the ADM is faster than another optimizer called stochastic gradient descent with momentum, aka SGDM. Then I will introduce you my training results. We can run our code now and to see what kind of diagrams, what kind of plots, the result accuracy the model will generate to us. We can leave our project for running now and return back to our result part. As you can see, when I set my epoch to 80 and the learning rate to 0.005, I can get a really high accuracy, approximately around 99%, and sometimes it will reach 99.5%. And the model performs well on clear emotions like happy and contempt, but confusion between similar emotions like fear and surprise, and sadness and anger. We can see the following confusion matrix to help us visualize which classes are most often misclassified. In the confusion matrix, the horizontal axis denotes the actual sentimental label. The vertical axis denotes the emotion categories predicted by the model, and the values on the diagonal indicate the number of correctly predicted samples and their proportion. The non-diagonal values indicate misclassification. In these two confusion metric images, we can see the left one. The model confused the sadness face with the anger face. Two sadness faces with anger faces. And in the right one, the confusion metric shows the model confused the fear face with the surprise face. And now we can get back to the model we ran before. As you can see, after 150 iterations, the accuracy becomes really high and stable, approximately to 100%, and the loss becomes really low, approximately to 0. We can also see the confusion part from the confusion matrix. As we can see, the model confused the surprise with fear, and also the surprise with sadness. The accuracy for this time is 99%. For now, we can see the results by live camera. The top two images shows the right prediction, but the bottom two images shows the wrong prediction. Well, according to my extensive testing, I found that the light condition will affect our result. As you can see on the left, I used the cooler light, but on the right, I used the warmer light. I found that when I use cooler light, the prediction is more accurate, but when I use the warmer light, the prediction is not that accurate. And when the light comes from the top light creates strong facial shadows. And even if I express mild emotion on my face, the model will misclassify my face with fear or anger because of the top light, because of the strong shadows. Let's go back to our live camera. As you can see, when I was wearing my glasses covered some part of my face, and the model cannot predict my face emotion correctly. After I took off my glasses, you can see that the prediction changes, but still cannot predict my face, my emotion correctly. I think it's because of the hair covered some part of my face. And for now, you can see that the predict I am surprised, which is correct. Well, in this study, I proposed a real-time face emotion recognition system based on deep convolutional neural networks. By training the model on the CK+ dataset with optimized hyperparameters, the ADAM optimizer, an initial learning rate of 0.005 and 80 training cycles, the system achieves a validation accuracy of 99.49%, effectively classifying 7 basic emotion categories when used datasets validation sets. The CNN architecture is augmented with dropout and batch normalization and exhibits strong generalization performance on the data on the validation set. Well, however, our evaluation also highlights limitations such as I mentioned before, the light condition and the insufficient occlusion. Well, the future work could focus on enhancing temporal analysis by incorporating video sequences, allowing the system to understand how emotions evolve over time rather than relying on single frame predictions. Integrating multimodal inputs such as voice or body language could also improve robustness in complex real-world scenarios. Optimizing the model for deployment on mobile or edge devices through techniques like pruning or quantization would broaden its practical usability, expanding training data to include more diverse facial expressions and exploring privacy-preserving methods like on-device inference are also promising directions. And here is all of my final project presentation. Thank you so much.